Okay, welcome back, everyone. Sorry for starting slightly later than 2:30. So we're very pleased to have a talk this afternoon by Shankar on more error correction magic. So this is actually the resolution of a kind of long-standing problem, the problem of constructing self-correcting memories in 3D. So I don't know anything about this problem except it was like all the rage when I remember being all the rage when I was a PhD student, and like people obviously didn't solve it, and now it has been solved. So very exciting.
All right, thank you. I would like to talk about this work, as Anand said, 3D self-correcting quantum memory. And I think the first question one might ask is, sure, it's been a problem that people have thought about, but why is this problem interesting or useful? And for me, there are three reasons why it's useful. The first reason is that it gives us some insight into a new way of doing error correction, a way of doing error correction that does not involve active measurements and dissipation. And it also maybe helps us progress towards building an actual quantum hard drive. The second motivation comes from quantum many-body physics. We know that quantum many-body systems can be very complex, and it's been a very long-standing open question to classify these quantum many-body systems. And so this gives some new and interesting behavior to many-body systems, especially in 3 dimensions, which is where our world is. And the last reason, which I find the most compelling, is that there's a lot of kind of fertile ground between kind of the following fields: geometry and topology, probability theory, statistical mechanics, and quantum coding theory. And I think that this work will push this fertile ground in some new directions and hopefully give us some new ideas that might make progress towards possibly other questions. Okay, so first I want to ask the question, what is a self-correcting quantum memory? And of course, we should start by asking, what is a self-correcting classical memory?
Can you write slightly on that?
Sure. Okay, so the self-correcting classical memory is a system of spins which interact in some way. They interact based on some energy function, which people often call the Hamiltonian. And the energy function depends on the configuration of spins, which I'm going to write as a vector S. And the way these memories work is that based on this energy function, the spin system interacts with an environment at some temperature T. Right? So what does this mean to interact at some temperature T? This means that these spins undergo some kind of Metropolis Hastings or Glauber dynamics, where the probability of some spin Si being flipped under the dynamics so Si is 0, 1 valued. So the probability of the spin flipping is going to be roughly equal to the energy of the spin configuration after the flip over the Boltzmann weight the sum of these two Boltzmann weights. Sorry. Okay. So this defines a Markov chain. It tells you if I want to flip this spin, the probability of flipping the spin depends on the relative energy of the configuration after flipping the spin over the total sum of the Boltzmann weights corresponding to before and after. And this Markov chain is defined in such a way that there is a stationary distribution to this Markov chain, pi, which is proportional to e to the minus beta e sub s. So this is just called the Gibbs distribution or Boltzmann distribution. But essentially the point is that this energy function dictates how these spins flip, the rate at which these spins flip, and these spins flip in such a rate that the distribution, stationary distribution, is a Gibbs distribution at some temperature. Okay. So right now I just talked about some classical dynamics of spins which flip under some energy function. So what is a self-correcting classical memory? Well, in order for a classical system to be a memory, there has to be some way in which I encode information in the classical system. So one definition that one can propose is that there exists encoding maps and decoding maps. So the encoding map will map a single bit into a configuration of spins, and the decoding map will, given the configuration of spins, determine what the value of the bit that was stored was. And so given an encoding map and a decoding map, and given an energy function, E, this defines a self-correcting classical memory if probability of the decoding process, the probability of this quantity. So what this means is if I want to encode a bit, I run some Glauber dynamics or some kind of dynamics for some time t, and then I attempt to decode. And if the decoded value is not equal to this b, we want this probability to be very small. So something like this, where n is the total number of spins. Yeah, n to the eta, sorry. Eta is some constant greater than 0, and n is the total number of spins. Okay? So basically, we want this probability of failing to decode to be very, very small, right? And we want this to be true, so I call this p-fail. We want this to be true up to times which are very, very, very long. So in fact, what I can do is I can define the memory time to be the time at which this quantity is, say, like 1 over 100 or 1 over 10. And in this case, if we have a self-correcting classical memory with this property, the memory time would be roughly exponential in theta of n to the eta. Right? OK. So this is an example of a system that undergoes Glauber dynamics. It thermalizes the environment, and it stores information for a very long time. Okay? So what is an example? Right? An example of a self-correcting classical memory is something that's, I guess, familiar to all of us. Yes?
Right. When you said it thermalizes with the environment, is that something from the map up here? Or?
Yeah. By thermalizes the environment, I just mean that undergoing Glauber dynamics, you eventually reach this distribution, which is a physicists model as some event where you've thermalized with the environment at some inverse temperature beta.
But do you require everything to be translation invariant or not?
Not necessarily, yeah. So a lot of the examples that people have are translation invariant, but you don't need to. Good. So.
Should I think of it as like actually thermalizing within the memory time, because then there's like a unique.
Good. Yeah. So actually you don't fully thermalize within the memory time, because if you look at the stationary distribution has equal weight on both of the encoded states, basically. So it's kind of like this is like a metastable state. You stay in this encoded state for a very long time, and then eventually, after this time scale, you completely thermalize. Good.
So you allow all the rules to be as complicated from the point of view of a function of their space and time as you want?
For this very general definition, yes. But then what we're going to do is we're going to care about things which are local in some constant number of dimensions. So for example, in the example I'm going to talk about, all of these update rules are completely local. So you can locally just determine all of these probabilities. Okay. So example is a very familiar model, the two-dimensional Ising model. Okay. It's a model of spins, which I will unfortunately write as bits on a two-dimensional lattice. So spins are normally -1, 1 valued. I will write them as 0, 1 valued. So I have a spin on each side of this lattice, and it either takes the value 0 or 1. And the energy function that I'm going to write on this two-dimensional lattice is a sum over neighbors, ij, on the lattice, put a negative sign here, to si. Okay. So this energy function is designed so that there are two states at the lowest energy. Okay. The lowest possible energy corresponds to the state when all the spins are 0 or all the spins are 1. So I'm going to call these the lowest energy E0, and this corresponds to all spins 0 or all spins 1. Okay. And there's a natural way then to encode a classical bit of information into the state. The all spins equals 0 state is just going to correspond to the bit being 0, and the all spins 1 state is going to correspond to the bit being 1. Right. And okay, so then the claim is that we have an encoding map. How about a decoding map? Well, to understand how the decoding map looks like, we can look at a typical configuration of spins in the two-dimensional Ising model. So if I have a configuration of spins, some of them are 0 and some of them are 1, I can view this as a bunch of zeros and maybe some islands of 1s, or vice versa. Right? And the zeros and the 1s are separated by things that we call domain walls. And the way the decoder is going to work is it's just going to identify all these domain walls. It can identify all these convex domain walls, and then shrink these domain walls. So in this configuration, since I just have a very small number of domain walls of 1s on top of a bunch of zeros, I can shrink these by the decoder, and I can decode this configuration into the all zeros configuration.
Wait, is there a reason you want to do this and not just take the majority of all the spins or something?
Yeah, so you can take the majority of all the spins. That's one way of doing it. But actually, if you want to prove this particular memory time bound, it's actually much easier to think about it in the shrinking way. But yeah, it can be any decoder, but the one we're going to pick has this property.
Wait, sorry, do you assume like locality for the decoder, or
A what decoder?
do you think it's local? Like, do you have to apply local?
It doesn't necessarily need to be, because the decoder is actually just going to be an artifact of the proof. So oftentimes it will end up being local, but we're going to just define this decoder so that we can prove this bound. So we're going to prove this bound using like standard like Markov chain mixing.
But you're talking about what's later? Or?
Yeah.
Okay.
Okay. So claim is that the memory time for the Ising two-dimensional Ising model, let's say the total number of bits is n, is exponential and theta to the n to the 1/2. Okay, so it satisfies this property where eta is 1/2. Okay, so how do we argue this? So there's a very nice theorem that again is standard kind of Markov chain type argument. So we're actually just going to compute the conductance of the Markov chain corresponding to this quantity, and then show that this conductance is exponentially small. So the way we do it is we define an unstable configuration S to be one in which when we apply a decoder to the configuration S, and try to decode the value, it does not equal the decoder acting on S plus a single bit error. So this E has Hamming weight 1, so it corresponds to like flipping a single bit. It corresponds to a single process in this in the Glauber dynamics, which flips the value of the spin. So these are configurations which are just on the verge of not being correctly decoded, right? And so what we can show is that the failure probability is less than or equal to t times something that's like order n times the probability under this Gibbs distribution at inverse temperature beta of of an unstable configuration. So we compute the total probability mass of all unstable configurations under a certain decoder. So this comes back to Nico's question. The decoder is kind of a tool that's used to prove this mixing time value. Okay, and then we show that this is, and then if you can show that this is exponentially small, then you're in business, because then you can show that the memory time is exponential in n to the 1/2. Okay, so how do we prove the unstable configuration? Well, one thing to note is that if a configuration is unstable, and I apply, let's say I create 2 domains of 1s, and I create a single error here, then I can accidentally coalesce these domains. I can accidentally make them very large, right? So an unstable configuration is one in which this domain of 1s is really, really large, and such that if I apply a single bit error, I will merge domains, and I will not be able to properly shrink these loops down to 0. Okay. So the probability of an unstable configuration yeah.
Sorry, I didn't follow. Why did that one move suddenly make such a big difference?
In this example, this move would not make a big difference, but an example in which it could make a big difference is if, like, you had kind of a giant domain like this. Okay, maybe I should. Which fills up like most of the system, and then you might accidentally, if I make an error in too big of a system, then the decoder might accidentally start cleaning up the domain in a different direction, basically. So this is a very large overcounting. Like you don't need necessarily, like, an unstable configuration is actually one in which you can. Like even if it has a big domain, it cannot be unstable.
I've now lost track of your procedure for decoding.
Yeah.
Okay, so
Yeah.
somehow it skipped past me that it was so unstable. So what was the?
Okay. Yeah. All I'm just saying is that if you had a decoding procedure, so the decoding procedure is just going to clean up domains which are small enough, right? And it basically won't work if these domains grows to be so big that they create too many 1s in the system, right? And in order for these domains to grow big, there must have existed a domain of some very large length in the system of 1s.
So sorry.
Yeah.
Is there? Can you say a little more precisely what this cleanup algorithm is?
Yeah. Okay. The way you do it is that you can basically you can draw like boxes around these 1s configurations, and construct like different connected components, and then you can. When you identify different connected components, which are convex, you can just apply a decoder that just shrinks it. Maybe another way of saying it is like it's a minimum weight shrinking procedure.
Sorry,
something.
is it a requirement that your decoder is local? Otherwise, like, wouldn't you just take the majority of the bits and?
Yeah, you can also take the majority. You can take the majority of the bits. I just think that like the way that people standardly prove these kinds of arguments is through a decoder that kind of just shrinks loops, identifies and shrinks loops. And yeah, the decoder is like the one way to think about the decoder is just that I have a configuration.
Can I just add something?
Yeah.
So what he's about to write down is that it's impossible for a configuration to be unstable unless there exists a large loop whose length is comparable with the system size. And it's the easiest to see that this is a necessary condition for a decoder to fail if you choose a decoder that relies on finding disconnected components of domains, as opposed to majority decoder. So it turns out that you can show that a decoder that works this way, the condition on unstable is very simple. It's a condition that if there is no big loops, it will never fail. Never satisfy this unstable condition. So if there's
It's like
no
a-
big loops,
it's a necessary
adding
property
extra
that
flip will
there
never
has-
make it go wrong.
It's like a necessary property that has to at least be a large domain of the other type, but it's not a sufficient property. Yeah.
You're saying that in majority, like, I mean, the majority decoder also has very simple failure conditions, the small ones. You're saying that this is somehow less easy to work with?
It's a less universal proof strategy.
Sorry, maybe you can just clarify what's the claim. The claim is that for any such decoder, for any decoder? Is that
Yeah, okay.
that-
Let me make the claim more precise, which is the decoder is just some very artificial thing. All I'm trying to do is I have some Markov chain and I have some graph of this is a configuration space, and I have some transitions between the different nodes in the graph, and I'm just trying to compute the conductance basically. So I'm trying to compute a region where the total probability of flowing from this region into the complement is very small. And the way I'm just doing it is the decoder is just some artificial thing that classifies some of the configuration.
These two regions, they are defined by the decoder, no? What
Exactly. So these are defined by the decoder. But the decoder is just like a technical tool that's used to just define these regions. So if I choose,
There exists a decoder such that that bound holds is like an exponentially small thing.
yeah, exactly.
Not be for every
It's
decoder.
not for every decoder. Yeah. It's just there's a particular choice of decoder. I can choose even a better one, and I can get a better bound. But it's sufficient to just find an example of a decoder such that this is.
But the majority
exponent.
decoder would work, no?
Sure, yes. But the issue is that for these topological codes, there's no such notion of a majority decoder. So I want to talk about it in this way because for quantum codes you can't just do majority vote.
But is there a statement that says if the decoder satisfies some property, maybe the one that Margarita said?
He's about to write that down, actually.
So it's, if the decoder satisfies this property about the long loops, then this is satisfied? Is this a claim?
Yeah.
So basically, if there is no long loops longer than, say, L/10, then it guaranteed succeeds. So that's the claim.
Yeah.
If you apply it many times? Or no?
Just once. So the point is that if the only loops, so first of all, loops have to be continuous and closed, right? Assume the system is on a torus. Then if every single loop that you draw in the entire configuration is length of L/10, then every single domain that loops must encompass must be on average convex, right? And if it's on average convex, then it will be correctly identified by the decoder, by definition of decoding strategy, because it fills convex regions. It classifies which parts are which this set of convex regions.
And is it easy to say what's on average convex?
I need to think about this.
Yeah, I think maybe one way to think about it is that if you want to identify a bottleneck, right, in the system, what you want to do is you want to consider a path that goes from, say, the all zeros configuration to the all ones configuration, right? So a path in this configuration space Markov chain. And it must be the case that as I'm doing these like little transitions, make these little transitions, I encounter a region in which there is a long or large domain wall, right? Because in order to go from the all zeros to the all ones configuration, you'll have to eventually nucleate a very large domain. And so basically you can compute the conductance essentially by just computing the probability mass of configurations where there exists some very large loop. It's a massive like overcounting, of course, but it's good enough for these purposes. Oops. Yeah. Okay. So it's just sufficient to just compute this probability, and the probability of this you can do. It's just by some union bound tricks. Is the number of possible loops of length L over 10. That's like roughly 3 to the L over 10 because it's just you're counting like self-avoiding blocks on the 2D lattice. Times the probability of having a fixed loop of length L over 10. And again, a simple estimate gives something like this. Right. So when beta is larger than some critical value, this is exponentially small. So with exponentially small probability, I've got to add the very important point that this is true for beta larger than some critical value. Of course, it's not true for all beta. But for beta larger than some critical value, this probability is exponentially small. And this means that the memory time is exponential in L. And L is roughly square root of n. Okay? Yeah. So I mean, this goes under, this is just like goes under the name of Peierls arguments. Like this is just standard stuff. Okay. Good. Okay, so I talked about the two-dimensional Ising model being a classical self-correcting quantum memory. So you can ask the question, what about the one-dimensional Ising model? Right? So I kind of skipped a dimension here. Right? So to do this in one dimension, right, we would, again, the reason why we're kind of saved is that errors form these domains, and the energy cost of these domains scale like the perimeter of these domains, right? So in one dimension, the problem is that if I do a similar kind of encoding scheme, and I create an error where everything is 0 here, but there's a band of ones, the energy cost is just the energy cost of these two endpoints, these two domains. So it costs very little energy in order to create this large error. So this means that under the Glauber dynamics, we would be creating these errors with very small. It's very cheap to create these errors. And what you can do is that under the Glauber dynamics, you can create a bunch of these little errors very cheaply. And these errors can grow and expand, again with 0 energy cost. And the fact that these grow and expand and diffuse causes a proliferation of ones in the system. And so it turns out that you can kind of actually rigorously prove that the memory time in the one-dimensional Ising model is order 1. So in the two-dimensional Ising model, something kind of important is happening, which is that there's a large suppression of applying an error to the system, because the energy cost of an error is proportional to the perimeter of this error domain. Okay. Okay. So this is what a classical self-correcting quantum memory is. Okay, but I kind of want to get to the title of the talk, which is what is a quantum self-correcting memory. So now, instead of dealing with some energy function in the classical case, we're dealing with a Hamiltonian, right? And a quantum Hamiltonian. And for simplicity, what we're going to restrict ourselves to is we're going to restrict ourselves to CSS stabilizer Hamiltonians. Right? So these are Hamiltonians, which are sums of stabilizer terms. Okay, so you have some lattice of qubits. These are subsets of the lattice. And this is some stabilizer defined on the subset. And because it's a stabilizer Hamiltonian, these commutes. Yeah. And the definition of a self-correcting quantum memory is to find, again, similarly, encoding and decoding maps, except the encoding map maps the state of a single qubit into the state of the system, which is, say, defined on n qubits, right? And the decoding map similarly does the opposite thing. So we define these encoding and decoding maps. We need to define them. And we also need to define a Hamiltonian H such that the failure probability, well, now instead of the failure probability, we're just going to write a statement like this. So instead of failure probability, it's going to be the trace distance between the dynamics where I encode the state, I run the dynamics for some time t, and I decode the state, and the original state. So I want this to be very small, basically. I want this to scale like t times a quantity which is exponentially small, which again, using a similar definition for the memory time means that the memory time is also exponential in some power of the number of qubits. But I'm not really specified this dynamics now, phi t. So this phi t is going to be some generalization of Glauber dynamics. So instead of doing Glauber dynamics like we did for the Ising model, we're instead going to run some more generic kind of open system dynamics. And this open system dynamics evolves in the following way. So if I have a density matrix, it's going to be some standard Hamiltonian evolution plus some term which corresponds to the interaction with the environment. And the interaction with the environment is often called the Lindbladian, and it takes the form So these are jump operators. So they're like the quantum generalizations of these updates that we do in regular Glauber dynamics. And if H is a stabilizer or CSS stabilizer Hamiltonian, then these essays can be made completely local. Right? But in general, these essays will only be kind of quasi-local. And importantly, these jump operators are defined such that the fixed point density matrix is a thermal density matrix at some temperature, inverse temperature beta.
What do you mean when you say these, you can make them strictly local?
I just mean that if this is a stabilizer Hamiltonian, then it's a very classical Hamiltonian, basically. So and if my jump operators are just x and z, then I can kind of determine the energy of the system in a local way, basically. Yeah, I don't know if that makes sense.
Does there exist in block dynamics the set of jump operators such that its fixed point is keep stable temperature data? Can have local jump operators and the fixed point will be there.
Yeah.
And for general Hamiltonians, you might need possible.
Oh yeah, of course. Yeah. But I'm restricting only to stabilizer Hamiltonians. Okay. Yeah, and yeah, so this 5T just describes this dynamics, and basically, we want this statement to be true for all temperatures, all inverse temperatures greater than or equal to some critical inverse temperature, which is order 1. Okay. So that's the definition of a self-correcting quantum memory. Again, you can encode this system, you can evolve under this dynamics, then you can decode the system, and it's very close to the initial state you wanted to encode.
Just for my understanding, like the
Yeah.
encoder is just the Hamiltonian, and the thing you describe is the encoder, the decoder, the critical temperature, and these assays.
Yeah. So the input is the Hamiltonian, the encoder, and the decoder. Right. You need to also discuss how you're going to encode your state in the Hamiltonian. Right. You can encode the information into just an arbitrary eigenstate of your Hamiltonian. Right. So the canonical thing is if H is a code Hamiltonian, you would encode it into the ground space. But you can do other things. Okay. All right. So yeah, the canonical examples that people study. When studying quantum self-correction is, as mentioned before, code Hamiltonians.
Sorry, the locality here is single qubit for the CSS codes? Or
You mean for the jump?
Yeah, for the jump operator.
Yeah, single qubit, for example. Yeah, but actually, in fact, like you can make these. At least for the examples we'll talk about, you can make these even more non-local, and you can still show that this memory property holds.
You mean for the examples that you constructed?
Yeah, but also for like the 4-dimensional toric code. Okay, so the canonical example of a Hamiltonian that we choose. So the trickiest part, of course, is picking the Hamiltonian. Because once you pick the Hamiltonian, since it's a code Hamiltonian, you can construct the encoder and decoder more easily. Okay. So the canonical example that people had studied was the 2-dimensional toric code. Okay. So the 2-dimensional toric code or surface code is a very standard code. It's defined on a lattice. The qubits are on the vertices. And there are 2 types of stabilizers. There's a stabilizer surrounding a vertex, which is called a star stabilizer. And there's another stabilizer people often call a plaquette stabilizer. And there are 2 kinds of logical operators. The first logical operator is a z-type logical operator, which goes across the system like this. And there's a dual x logical operator, which goes across a system like this. So when I say goes across a system, I mean it's a tensor product of all the z or x operators that touch these links. That goes across. Okay. So when you try to compute the memory time of the system, you'll find that it suffers from the same problem as the 1-dimensional Ising model. Okay? So what was the issue with the 1-dimensional Ising model? The issue was that it's very cheap to create a large domain of errors in the system. It costs very little energy. And in the two-dimensional toric code, something similar happens, which is that I can create a very long error string here, and it costs very little energy. It only costs an energy corresponding to the two stabilizers at its endpoint that it violates. And for a similar reason, generically, when you run this Glauber dynamics, you'll create a bunch of these small strings. These strings can move around and diffuse and connect together and percolate into a long logical operator. So as a result, the memory time for the two-dimensional toric code turns out to be order 1. Okay, so there's something called the four-dimensional toric code. And the four-dimensional toric code can be defined the following way. So for the two-dimensional toric code, there's a nice thing we can notice, which is we can divide this square lattice into cells. We can divide them into 0 cells, which are vertices, 1 cells, which are just edges, and 2 cells, which are plaquettes. And each 2 cell is associated with a stabilizer, a Z stabilizer. Each 0 cell is associated with an X stabilizer, and each 1 cell is associated with a qubit. So I can make the identification. A 1 cell is a qubit, a 0 cell is an X stabilizer, and a 2 cell is a Z stabilizer. So in the 4D toric code, we are now on a 4-dimensional like hypercubic lattice. So now there are 0 cells, 1 cells, 2 cells, 3 cells, 4 cells. And what I can do is I can place qubits on the 2 cells. I can place X stabilizers on the 1 cells, and I can place Z stabilizers on the 3 cells. And this defines for me a stabilizer code. Okay. So this stabilizer code has a very nice property, which is while in the two-dimensional toric code, the logical operators are strings, in the four-dimensional toric code, the logical operators are membranes, basically. So this means that, so I'm drawing this in 3 dimensions. But in order to apply a logical operator, I have to apply an operator geometrically supported on this membrane surface. And this is very similar to the two-dimensional Ising model. And the reason why it's similar is that if I apply an error in the quantum code, the syndromes that it violates are localized in the boundary of this error domain. This is exactly the principle that worked for the two-dimensional Ising model. Right? And because these are the energy cost is like the perimeter of this domain, we can apply exactly the same argument in the classical case. There, we can't do a majority vote decoder because this is a quantum code. So there we're actually doing a decoder which is like some minimum weight kind of loop shrinking process. And then you run a Pyrrhus argument, and you can show that for the 4-dimensional toric code, the memory time is exponential in theta of n to the 1/4. It's n to the 1/4 because the linear length of the system is a 4th power of the number of qubits in the system. Okay, so I told you that the 2D toric code doesn't work. And the reason it doesn't work is because there are logical operators that are string-like. For the 4D toric code, there are no logical operators that are string-like, and it is a self-correcting quantum memory. So there's clearly a gap between the 2D and 4D, which is 3 dimensions. And so one can ask, is the 3-dimensional toric code closer to the 2-dimensional toric code or the 4-dimensional toric code? And it turns out that for X operators or X errors, it's very close to the 4-dimensional toric code. But for Z errors or Z operators, it's very close to the 2-dimensional toric code. And so because of this, the memory time is going to be theta of 1, order 1. Okay. So quantum, yeah. So it's still a classical self-correcting memory because it's good in one of the sectors, but it's not good in both sectors. Okay, so then there's a bunch of different kind of ideas that people put forward to how to maybe construct a three-dimensional code, which is a self-correcting quantum memory. There is a code proposed by Haab, which is called the cubic code. And for reasons maybe I don't have time to talk about, that one doesn't work. There is a code that was proposed by Michinitsky called the welded toric code. This one also doesn't work. There's a code proposed by Brel, which involved taking homological products of classical codes and put it in fractals. That one also doesn't work. And there are some recent developments in codes in 3 dimensions which saturate bounds on kind of the best possible parameters, and such as like layer codes. And unfortunately, also layer codes don't work. And they all kind of don't work for like a philosophy that's similar to the fact that it's very energetically cheap to create kind of large errors in these codes. So unfortunately, it's been kind of a challenge to construct an example of a self-correcting quantum memory in 3 dimensions. Okay. So then our result is that there exists a self-correcting quantum memory in 3 dimensions. So there exists a family of Hamiltonians. K indexes the size of the family such that the memory time scales exponentially in the number of qubits at that scale, and the code is local in 3 dimensions. Okay? And by local, I mean that all of the interactions are local, and also the code has a bounded density property. There are not too many qubits occupying a unit ball in R3. Okay? And yeah, the last fact is that the code is perturbatively stable to Hamiltonian perturbations. But this was not in version 1 of the paper. This proof of this will be in version 2 of this paper. Okay.
Can you say what that means a little bit?
Yeah. So what perturbatively stable means is if I take a Hamiltonian H and I add a small perturbation to it, epsilon v, then if I want to encode a qubit in the ground space of H, there exists a kind of an interpolation. Just think about it as like applying some adiabatic algorithm that interpolates between the ground space of H and the ground space of H plus epsilon v. And this adiabatic kind of interpolation works for any local perturbation v as long as epsilon is smaller than some universal constant. Okay, so this is like a nice property that says that the self-correcting memory is stable against Hamiltonian perturbations. We didn't prove that the memory time is stable under Hamiltonian perturbations. That's actually still not known for the 4D toric code, but it's definitely probably true. Okay.
So what you proved here is the same stability
like Bravi, Hastings, McLaughlin, yeah.
So Shankar, there was a request for like a 2-minute break
Yeah.
in the morning.
Yeah. Let's do that. Yeah, I guess we can do that right now.
All right. See you in 2 minutes then.
Don't waste energy.
Okay. Welcome back. So let's carry on with part 2.
Okay. Yeah, okay, so I kind of stated the result, but now I want to kind of explain how the construction really goes. And I think an illustrative way to explain the construction is to explain an analogous classical code. So we came up with an analogous classical code, which I think has or gives enough of the intuition that once you see it, you'll be able to kind of understand how to construct the quantum code. So the observation, or at least the strategy that was kind of an issue with all of the other examples in 3 dimensions, is the existence of string operators, right? So we want to avoid string operators. And we also want errors to kind of look like how they look like in the Ising model. So if I have an error domain that I've applied, the energy cost of that error domain is going to be very large. It's going to scale something like the size of the domain. Okay. And the way that we're going to achieve this property is we're going to do things in a multi-scale way. Okay? So what do I mean by multi-scale? Well, I mean, I'm going to start out with a very, very small code, and I'm going to do an amplification process. I'm going to grow the code and amplify the energy cost of certain errors. And I'm going to repeat this procedure many, many times, so that if I have a large error, that will naturally come with a very large energy cost. Okay. So I'm going to illustrate this multi-scale approach in an analogous classical code. So the property that I want of the classical code, which I'm going to figure out why it's useful later on, is I want the classical code C and the transpose of the classical code to be self-correcting, classical memory. Okay. So why do I want C and C transpose? Well, it's going to be useful to develop a classical code with these properties, because you can think about the X errors of the quantum code as feeling C, and the Z errors as feeling C transpose. I'll explain why this is actually true in the quantum code. But for now, let's just assume that we want to find a classical code with this property. Okay? And we're going to build the classical code, again, in some recursive way. And the recursive way in which we're going to do it is going to be very reminiscent of the idea of Tanner codes. So in a Tanner code, the idea is that we have a code specified by some geometry. So we have some graph that specifies some geometrical aspect of the code. And we have local codes that we place on the vertices of the graph. And together with the geometry, the specification, the local codes gives us some interesting properties, right? So this is how people constructed things like the Sipser-Spielman codes. Okay. So the local codes that we're going to care about are actually going to be very simple. Okay? So it's just going to be a repetition code, which I'm going to denote by a black dot. And the repetition code, so the bits are going to be on the edges. And the local parity check matrix, the repetition code, is just going to be going to look like this. And the other local code that we'll care about is something that's called a parity code. And the parity code will have a local parity check matrix, which is just 1, 1, 1. So the code words of this local parity code are basically all bit configurations which have even parity. And of course, the code words of the repetition code are the all ones or the all zeros. Okay. And okay, so I discussed the local codes. So now let's discuss how to combine the local codes with the overarching kind of graph structure. So I'm going to construct the classical code through a couple of steps. Step 0 is we start with a very simple code. The code is just going to be a repetition code in 4 bits. So I'm just going to denote it like this. Right? So I'm just going to diagrammatically denote it like this. And step 1 is I'm going to replace each edge with a local structure. Okay? And what is this local structure? Well, the local structure is going to be, I'm going to replace this edge with a ladder, basically. And this ladder is going to have, in this case, all repetition defects. So you can think about this as just a repetition code, but on a geometry which is a ladder geometry. Okay. All right. So there's one thing, additional thing that I have to specify, which is if I had a trivalent vertex like this, how do I do the replacement? Because I need to discuss how to do the replacement near this trivalent vertex. The way I do the replacement is I draw the three replaced ladders, and then I kind of triple-wise connect these vertices together. So kind of do this in like kind of a sort of transversal way, so to speak. So this is how I do this. And the second step is to repeat 1 many times. Okay. All right. So one thing that I'm not specified is that the ladder will have some length L. Okay? And this L is just going to be a constant. It's going to be order 1. But it's going to be important for the purposes of embedding. So the larger the value of L, and this value is like 1, the more one-dimensional the code will look. So this is going to be a code which has a fractal dimension 1 plus epsilon, but the epsilon is going to be dependent on how large I make L. I just need to make it just some large constant.
So just to make sure I understand, this is, you just dimension code, you basically don't
Exactly. Yeah, exactly.
So far you haven't used the.
So far I've not used it, yeah. So I just want to, I want to just provide some intuition for what's happening here, right? So what is the intuition for what's happening? Well, if I have some, have this replacement procedure, and let's say I have an error on this bit, well, this error will kind of violate syndromes on this local code and some other local code on the other end of the error. And what I can do is, under this replacement procedure, I can lift this error into essentially a local code word on this ladder, basically, this ladder structure. So the local code word on this ladder structure will just be, say, all ones everywhere in the ladder, basically. Right? So the two local code words of the ladder are all zeros and all ones. So the local code word, if I turn this 0 into a 1, then it's kind of equivalent. There's a map that maps this onto a code word where I flip all of the bits on this ladder. Okay? And one interesting thing is if the syndrome of this error, the weight of the syndrome of this error is, if it's 2, then the weight of the syndrome of corresponding to this error has doubled, right? Right. So because now it violates syndromes at these two codes, and two codes here. So this doubling property is very important for us. Okay? It essentially means that when I repeat this procedure many times, say k times, then the image of this error would have size c to the k, right? Because under this map, this image of the error gets multiplied by some constant factor c. But it would have syndrome weight, which is 2 to the k, right? So error with weight c to the k has syndrome with weight 2 to the k. Okay? And this is a very good property to have, right? It's similar like in the Ising model. If I had an error of some size, n, it violated syndromes, which is a power of the size of the error. So this is a very nice property to have. But unfortunately, it's not enough to solve this desired question, right? And why is it not enough? Well, let's say.
Which desired question?
Yeah, the desired question is C and C transpose a self-correcting classical memory, right? So I'm going to argue that this is enough to show that the code C is a self-correcting classical memory, but C transpose will turn out not to be. Okay? So what does C transpose correspond to? Well, C transpose corresponds to replacing repetition defects with parity defects and vice versa. Okay? So actually, to see it's not quite the same as this. It's approximately equivalent to it. But I can talk about this in more depth, but it's geometrically roughly equivalent to doing this. Okay. And what's the issue with if I replaced all of these black defects with white defects? Well, I have a similar circumstance where all of these are now white defects. And this code splits. But now, when I create an error here, this error gets mapped onto a local code word of this ladder. And one of the local code words of this ladder is just a error that just goes across one of the legs of the ladder, unfortunately. Because this local code word corresponding to flipping all of the bits along this edge, it satisfies all of the checks here. So creating error here is mapped onto creating error only on one of the legs of the ladder. So this no longer doubles the number of syndromes, right? So the syndrome, if this costs syndrome, which is, say, 2, then under this map, this also costs syndrome, which is 2. And so you'll have an error as you continue repeating this process. There will exist an error which has weight c to the k, but has only syndrome cost 2, basically. So this would be a string operator, basically. It's not something that we like to have in this code. And in fact, you can show that this C transpose code is not self-correcting. Okay? So how do we fix it so that both C and C transpose is self-correcting? The solution is actually very simple. It's we have a first step where we replace each edge with this repetition ladder. Then we have a second step where we replace each edge of this corresponding code with not a repetition ladder, a parity ladder. So we actually alternate between applying a repetition replacement and a parity replacement. And step 3 is to repeat step 1 and 2 many times. Okay. So what does this achieve? You can write the code C as a replacement of repetition followed by a replacement with parity some number of times k, acting on some initial code. I'll call it C naught. Yeah. All I was saying here is that for if I want the property that both C and C transpose are self-correcting, and C was just doing repetition, just doing this part many times, then the transpose would just be doing this many times. And so the transpose code will have very bad properties. So the key is actually to kind of interlace them, basically, to alternate between doing them. Because C transpose is essentially going to be just, I just replace the repetition with parity and vice versa. And the nice thing is that during the repetition step, I still am doubling the weight of the error. So since I'm doubling the weight of the error during the repetition step, if I have an error of size c to the 2k, after doing this 2k times, so this is an error, the syndrome, the size of the syndrome, is still going to be 2 to the k. So it's still growing as a power of the weight of the error. So this is okay. So this is actually very important, and this is actually going to be how our quantum construction is going to work. So our quantum construction is going to work because you can think about this as a procedure for improving properties of X errors. This procedure is not going to do anything to X errors, but instead it's going to improve properties of the dual errors, the Z errors. And by alternating between these two procedures, we'll have a quantum code with very good properties. In fact, it will be self-correcting, both for X and for Z errors.
Why do we need to alternate
Yeah.
again? Why do we need to alternate again? Why can't I just do all of one and all of the other?
You mean like why? You mean just do repetition k times followed by parity k times? Yeah, it's because if I were to do something like this code would be okay, but if I were to take the transpose, then I would get, like, after doing this k times, I would get an error which costs very few syndromes, which is very large, is of size c to the k. So you kind of it's like when you grow the code by a constant factor, you need to ensure that you double. Like here, if I grow the code by a factor c squared, I'm doubling the syndromes of both X and Z errors. So I can't just like do one for a large amount of iterations and then do the other. I kind of have to actually alternate between doing them. Yeah.
So I lost some of the context. Like, are you currently trying to do an analysis in 3D or?
No.
Okay.
No. Currently, all I'm trying to say is that I'm trying to construct a classical code with this property,
Okay.
and it has nothing to do with the quantum code yet. So
Okay.
I'm going to eventually relate this to the quantum code, how the
So
quantum code is going to work.
We're still in 2D, or?
Yes.
Okay.
We're still in 2 dimensions. Yeah. Yeah. So this is and also this is still classical. So I've not said anything about the quantum code. I'm just giving intuition for how the quantum construction is going to look like. Yeah. And there's one more claim, which is that this code admits an embedding into 2 dimensions. I'm not going to talk about that claim too much, but there's one more step that you can do, which is an embedding step, which allows the code to be local in 2 dimensions.
So the only problem is this defect, the bridge there.
Yeah, exactly. So what you have to do is you have to somehow stretch this edge a little bit and then kind of push it, flatten it into 2 dimensions. And then, so by just some amount of distortion, some constant amount of distortion, you can get it into 2 dimensions. Yeah.
So does this show that like an arbitrary configuration of a certain energy has a number of syndromes? Or which is...
Yeah. Well.
Here's just for a very specific...
Yes. Yeah. So this is just an intuition for why it's true, but in fact, you can show that for any configuration with a number of syndromes, it has to, any configuration of some size, it has to cost a lot of syndrome.
What
So
does the argument look like?
Yeah, the argument. Okay, so actually, I was going to outline the argument more towards the very end, but maybe for the sake of I don't know if I'll have time to do it, but essentially, if I have some error, I can basically apply a small correction operation so that the error is in a coarse-grained location. So whenever the error is in a coarse-grained location, then I can show this very nice like doubling property. And what I can do is I can show that whenever I can there always exists a correction which only decreases the number of syndromes in the error. So basically, the error would have to cost more syndromes than the coarse-grained one, and the coarse-grained one already costs a lot of syndromes, so that's how it works.
Can you explain again this, it looks like it's non-planar, and no matter how you.
Yes, okay. Good. So how do you make it planar? Yeah, so So what I'm going to do is I start with this code. I'm going to first scale this code by some amount, which is this L. And then what I'm going to do, I can view this replacement procedure as taking another copy of this object like this, and then placing a bunch of rungs between the two copies of the object, essentially. Right? So you can think about this as replacement because, so this is kind of, this is a little distorted, but you can think about this as a ladder. And the connection of these 4 ladders together is exactly seen in this replacement procedure.
What do you do about this?
Good. Yeah, so this part, right? So what you can do is you can further just subdivide this segment into 2 parts, basically. And this subdivision, it only changes the, it changes the ladder by basically, instead of a ladder like this, you might have a ladder like this, or something like that. And adding this extra repetition here doesn't affect the properties of this code. You'll still have this doubling property. So then in the next step, what you do is I scale the system by another factor L. I take a second copy of the system, I shift it by a little bit, place it on top of the first copy, and I add a few more rungs in certain locations. And then the specification of the local codes just is related to whatever step you're on in the procedure. Yeah. So there's some, yeah, and basically just there's some kind of brute force analysis, but like you can kind of show that there are no intersections and stuff if you do it this way. Okay. Actually, I don't want to erase that.
I think more factor statement is that most order one things intersect. Also maybe a small comment to Ethan's question. You could show an even stronger statement that configuration is drawn there, like the larger one, is actually a local minimum of energy for error size. So like if I deforming it a little bit away, it will only increase energy. Then you'll shrink it very much, then you the energy will become smaller. But then there will be again this argument.
Okay, so for the quantum code, I don't have very much time, but so I will go through this relatively quickly. So the way I want to construct the quantum code is by doing something very similar, writing down these analogous local classical kind of codes. And the way I'm going to do this is by using some well-known results related to defects of the toric code. So essentially, there's some very nice properties of the toric code. One property is it admits. So I can take, let's say I take a patch of a two-dimensional toric code. I can take this patch and I can glue it to 2 other patches, and I can glue it in some consistent way so that the logical operators have the following property. So if I have an X logical operator, the X logical operator goes through the code, but it can go through, it goes through one code and it goes through only one other code, right? Or it can go through this code, or it can go like this, right? So one nice thing is that this looks exactly like a parity defect, right? So it's kind of the parity of the logical operator is even, basically. If I look at the dual logical operator, the X logical operator, is forced to split like this. So while the Z logical operator sees this as a parity defect, the X logical operator sees this as a repetition defect. Okay? So this is a very specific kind of defect. I can write down a stabilizer model for this, but the Z logical sees this as a parity defect, and the X logical sees this as a repetition defect. There's another defect of the toric code where the opposite happens. So the x sees that defect as a parity defect, and the z sees that as a repetition defect. So now the intuition should hopefully be clear. The reason why I cared about this question should be clear, right? Which is, I want the self-correction property to hold for both z and x errors. So if I construct a network of these defects, I want to have this self-correction property for z. And in order to also have the self-correction property for x, the transpose effect must also be true, right? The effect where I replaced parity with repetition or repetition with parity must be true. So just like in this case, the way we solved this problem was that we constructed a procedure that first did like some amplification, some repetition step, and some parity step. So we're just going to do something very similar here. We're going to so the quantum construction is going to have the following steps. We're going to start with a very simple code. And the code is just going to be like a surface code on 5 bits or 5 qubits. So it's like these are the qubits, and then there's going to be some x checks and then z checks. So this is just a diagram of a Tanner graph, but you don't need to know about what this notation means. You just need to know that this is just some very small surface code. Then, just like how it was done in the classical case, we're going to do a replacement procedure. And now the replacement procedure is going to not concern edges, but it's going to concern these like plaquette variables in the surface code, right? So when I have something like, okay, let me just write this like this. When I have a plaquette variable like this, I'm going to replace it.
Sorry, I missed it.
Yeah.
Are you explaining how do I read this diagram? Like
Yes. The black vertices are qubits. The x is an x stabilizer. Its support is the black vertices that it's connected to. Sorry, I should draw these lines. And the z are z stabilizers, and their support are black vertices they're connected to. And so what I do is I replace some local structure of this Tanner graph with something that kind of looks like this. So I'm just going to draw a figure and then quickly explain why it looks like this.
Sorry.
Yeah.
Can you explain? I'm a little bit confused. You started from this construction for C and C transpose classically.
Yeah.
And I thought you're going to use this for the quantum.
Yeah.
Are you going to use this for the quantum, or?
I'm not going to directly use this, but I'm going to hopefully show you that what's happening here is actually very similar to what's happening here in the classical case. Yeah. There's one way in which you can directly construct a quantum self-correcting memory, which is I can take a hypergraph or product of the classical codes corresponding to C and C transpose. That already would have the self-correcting properties. But this code is harder to analyze. This one is easier to analyze, it turns out. But the idea is similar. The idea is a replacement procedure where I replace in the classical code an edge with some local complex. In the quantum case, I'm replacing some plaquettes basically with a larger local complex. And yeah, so the local complex looks like this. And geometrically, you should just think about this as two L by L surface codes, which are connected by two kind of defects, basically. So again, like whenever I draw this whenever I draw this kind of structure, it's a defect of this kind. And I connect them with these defects. And when I draw logical operators, they have the following property, that if I try to draw a logical operator here, if it's a particular kind, say the X logical operator, it will split into a repetition. It will behave like it does in the repetition defect, and it will be kind of forced to double, basically. So when I take a logical operator, and then I consider its image under this map, it costs twice as many syndromes now, basically. So this doubling property occurs now for one kind of logical operator. And then for the other kind of logical operator, because these defects it sees are like parity defects, nothing will happen, right? You won't have this doubling property. So I'm going to call this procedure Rx. And during the second step, I'm going to define a similar procedure Rz, where basically x and z are both interchanged. And when x and z are both interchanged, the opposite happens. So here, the x logical operator had the syndrome doubling property, but here, the z logical operator would have the syndrome doubling property. Actually, I think I flipped this. I think here the z logical operator has a syndrome doubling property, and the x does in the other case. But essentially, one of them will have a doubling property, the other logical won't, and that's very analogous to in the classical code C. During this step, the syndrome would double, but in C transpose, this would be replaced with parity, and this one will not double. And so the quantum code QK can be obtained by taking these two replacements and just alternating between them some number of times, and acting on this initial quantum code. So that's the full construction. There's one last step, which unfortunately I don't think I have time to explain, which is the step in which one argues that this code is embedded locally in R3. And the way this step works is that I need to define step 1' and 2'. And along with this code, Q sub I also need to define an embedding map. So this embedding map maps this graph into R3 in some local way. And during 1' and 2', I need to do a step which I call perturb. And this perturb is a step where I have to, in some smart way, randomly move around vertices and change the embedding map, right? So I apply this replacement step, and then I change the embedding map by this perturbation step. And this is necessary in order to ensure. Yeah, it's a little complicated. I don't think I have much time to talk about it. But essentially, it's a step in which, when I do this replacement procedure, this map, the density will increase, basically. What do I mean by this? I mean, when I apply this procedure, I added more qubits, I added more cells. And so when I just naively construct the image of this in R3, there'd be regions where the density has increased. And the perturb map is a map that, in some particular way, moves around vertices in such a way that these high-density regions are lowered a little bit. So it's hard for me to explain without going into more detail. But fortunately, I don't think I have much time to do that.
This is where you lose translation invariance?
You lose translation invariance essentially everywhere, right? Because I'm even during the first replacement step, this is no longer a translation invariant. But of course, yeah, especially you'll lose translation invariance in the perturb step because you're doing a random perturbation.
The type of perturbation is discrete, or I'm trying to understand what is it that?
Oh yeah, it's discrete. It's some procedure in which you color the vertices of your graph, and then you pick vectors on some sphere, on some unit ball, and then in some random way, based on the coloring scheme, and then you shift the images of these guys in R3 by a vector randomly selected in this ball.
In order for this to be embeddable in R3?
Yes. Because unfortunately, if you don't do the perturb step, what's going to end up happening is the density of qubits is going to diverge, basically. Because you can think about this step as I take a square, and then I add another copy of a square on top of it. And so if I keep doing this many, many times, I'm kind of packing a lot of squares on top of each other. And if I do this k times, the density is going to be proportional to k. And that's not what we want to do, because k is going to scale with the number of qubits in our system. So we need to kind of push these planes away from each other in some particular way in order to fix this. So that's a perturbed stage. Yeah, I'm happy to talk about it more offline, because I don't. But the definition of local in R3 is both locality of the interactions and density, basically. Because what I can do is I can take, like, if I have the 4-dimensional toric code, this is like a 3-dimensional shadow of it, and this is the 4th dimension. I can just do a trick and just like flatten the 4th dimension down. So all the interactions are going to be local, but now there's going to be some like order L number of qubits on each side. So you can like cheat and say something that's not local in 3 dimensions is local if you don't include the bounded density.
Will you get to talk about the decoder?
I'm probably out of time. Okay. Yeah. I just don't want to. I don't know. It's just, I can talk about the decoder, but you guys should stop me if I'm taking too much time. Okay. Good. Okay. So. Yeah.
Sorry, about the embedding, Margarita's comment from earlier that in fact there's O of 1. You sort of don't care about the O of 1 every time.
We don't add them on top of each other. We show that it doesn't accumulate. It's at unit scale. At most O of 1 things sit on top of each other always.
And this doesn't work here? You still need to handle this embedding issue, and you do that with
Yeah, so actually there are two methods for doing embedding in our paper. So the second method is actually very similar to the one I mentioned in the classical code. Like we had some deterministic procedure where you like shift something by some amount and then add rungs. So there's some gadgety way of doing it, but it's very complicated. The way I'm talking about here is a little easier to talk about because it's a random method, basically. So we just say we randomly perturb things, and this is what people do in like geometry. Some metric geometry people do this, and then you argue by some like Loas local lemma that there doesn't exist bad events where the density is too large.
I think I understood the question. I think what you mean is, like, if I embed it and now 2 things overlap, the question is, can I just keep doing and maybe 2 things will keep overlapping? The problem is that, so if I have 2 like squares that overlap, now if I substitute that construction into 2 squares, I will have 4 things that overlap. And after I do it k times, there will be 2 to the k.
And you can't perturb.
Exactly. So if I didn't perturb, if I don't do anything about it at each step, it will keep accumulating actually.
Okay. Okay. So so then I want to mention a little bit of the proof of the self-correction property. Okay, so there's one thing I'm not going to talk too much about, which is the part that uses some homology theory, which is just that every time I perform this replacement procedure, you have to argue that the dimension of the code space doesn't change. So essentially, what you can show us through some homology theory is just that the dimension of the code space doesn't change if I keep repeating this procedure many times. So if I started out with a code that encoded like a single logical qubit, then I'll end up with a code that also encodes a single logical qubit. Okay. So the proof of the self-correction property is the part I kind of want to focus on. And yeah, just kind of like before, the probability that the encoding, evolving, decoding procedure fails, kind of bounded this by some t times some quantity that was like theta of n times some quantity which was the probability of an unstable configuration under the Gibbs measure, right? And in order to define these unstable configurations, you need to utilize a decoder. So the nice thing about the quantum code is because this procedure is recursive, you can also use a recursive version of a decoder, right? So the decoder, D, is going to act in many stages. It's going to be like a bunch of decoders which act on different scales of the system. Okay. And what exactly do these decoders do? So again, I want to make some analogy to the classical construction, and the analogy is going to be as follows. So what I do is, let's go back to this like classical code construction, and let's say I had some code, the part of the code, piece of the code that looks like this. Then under this replacement procedure, I will have this will turn into, some structure of ladders. And let's suppose for simplicity that these are all like repetition defects. So these are all repetition ladders. So what's going to happen is, as I mentioned, there's a natural map between an error on this edge and a local code word that spans this entire kind of complex or structure here. Right? So there's a natural map between an error on this edge and kind of a logical error in this. And what the decoder at this scale is going to do is it's going to find, so of course, I don't necessarily have an error configuration that's exactly like a logical operator in the restricted G here. It can be some weird error configuration that's kind of only partially forming a logical operator. So what the decoder is going to do is it's going to map some error at scale k into a correction operation such that ek plus ecorrect is what I'm going to call a sort of canonical error. So now the canonical error is going to be entirely supported on this local code word. And then what I can do is I can lift this canonical error to an error at scale k plus 1. Right? And so this is how the decoder is going to work. And then the decoder has an additional nice property. And the property is that if this error had syndrome sigma k, and the decoder cleaned this up into some canonical error configuration, then the weight of the canonical error configuration is less than sigma k. So the decoder, there exists a decoder which has this property that it sends an error into some canonical error, and the canonical error always has a weight which is less than or equal to this error. So then, when I kind of lift this back into an error here, called this syndrome configuration sigma k plus 1, I'm going this way, the other way. Yeah, okay, fine. I can. It doesn't matter. Okay, k minus 1 or k plus 1. It's less than or equal to, sorry, it's equal to the canonical syndrome weight divided by 2. So this essentially means that the syndrome weight upon applying the decoder and then lifting into this copy is less than or equal to 1/2 the weight of the syndrome. So the weight of the syndrome at the kth stage is divided by 2 is greater than the weight of the syndrome at the k+1 stage. And so, okay, this property for the decoder is actually very important and very useful. Right? Why is this important? Well, it turns out that an unstable, going all the way back, we can define an unstable configuration in the following way. So let's say that I have a code. I have a code at some level k. Yeah, maybe I should write this as k minus 1. Right. So I define an unstable configuration as one in which if I have some error that occurred at level k, under like this iterative application of the decoder, the error got smaller and smaller and smaller, but it still remains, there's still some error, there's still some remnant of it at level 2. So if you have an error for which this is the case, then that's how I define my unstable configuration. So this computation is just computing what is the probability of an unstable configuration, or what is the probability that under this particular kind of decoder, I still have a remnant of the error left when I've performed this process, all the way up to level 2. And you can use the property, this particular property, the decoder, how it reduces errors, in order to basically argue that the probability of this is exponentially small. Yeah, I mean, I can go over some details about that, but I don't know if this is too important. But essentially, the important part is you can define your decoder to be operating in this multi-scale way, and then you can show that the decoder reduces the weight of the syndrome. And if if there's still a syndrome left at level 2, it must correspond to a very large syndrome at level k. And then the probability of having such a large syndrome at level k, you can show by some Peierls argument that is exponentially small. Yeah.
How does this perturb replacement map affect the way your decoder works? Or is there any?
Oh, the replacement map. So you can, so basically so the way the decoder is going to work is there's some error configuration here. It's going to apply a correction that kind of cleans this error to some canonical location. And then you're going to apply a map that lifts this onto an image in the code at the previous level, right? So this map essentially recursively tells you this map kind of contains the necessary information about error configurations. It essentially tells you that all the error configurations here correspond to certain kinds of error configurations here, and the decoder basically maps you to the closest candidate error configuration, which is well defined under this map where I lift from this to this. So that's how this step enters in the decoder, and the doubling procedure enters because of this factor of 2 essentially. So the syndrome at this level is smaller by a factor of 2. So if you have a syndrome that's still present at some level 2, this corresponds to some very, very, very large weight syndrome. And because it's a very large weight, it costs a lot of energy, and then that's how you can run the Peierls argument. The perturb step doesn't do anything, because the perturb step is just like a geometry step. It just tells you where your qubits and checks are positioned in space. So you can just forget about that, and you can just think about the decoder acting on just like the Tanner graph of the code.
the classical construction also from your work?
Yes, yes, yes. The classical construction also has some it has some very interesting properties. I think more interesting to physicists, but yeah, I can tell you about it offline. Yeah. Yes, yes. I feel like I'm taking too much time.
Maybe we can call it here and ask Shankar more questions over the reception, but thanks for a great talk. I think so, yeah, it should be right outside.
Outside.
Yeah, I think they want us to